Hi and welcome back. This is clip 17 on wind generation. Now I've made an earlier video 17 but I didn't have the same props. I'm remaking it. I'm going to take it down and replace it with this one hopefully. Now one of the reasons for getting this, we need to get it very straight. What is the contribution of wind energy? And indeed what is the contribution of wind and solar energy and all those things? And it's hotly debated. But the fact is we have 3,400 megawatts of wind energy in Ireland. That's equal to average demand. And we're not saving any CO2 emissions. We're being constantly told it hasn't worked, that we have to do something else to meet our targets for 2020. So we need to look and see how that can be. Now the first thing to remember about the grid system is that it's a machine. It is not a political thing, it's a machine. And if you buy a sewing machine, you'll read the manufacturer's instructions and you'll go by them. If you buy a video camera, you'll do the same. But there seems to be an idea that those who make electricity by means of fossil fuel are not well placed to comment on how it's made by renewable sources. And this conflict is based on the mistake that this subject is intuitive, number one, and that it's political, number two. It is not. The electricity grid is nothing different to a lawnmower, a tractor or a car, a sewing machine, a watch that you wind up, or anything else. It's a machine. And it behaves like a machine. It's not, hasn't a mind of its own. It's a machine. That has to be got into people's heads, because there's a lot of people saying, oh, you can't read the instructions, you can't do this and that. So what is the situation with mains electricity? Well, the first thing to remember is that it has to be on all the time. You have to have power 24/7, and that means 8,766 hours, 8,766 hours in the year. And there's 60 minutes in an hour and 60 seconds in a minute, and the power supply alternates from positive to negative 50 times per second. Now you can count that up yourself. It's 8,766 multiplied by 60 multiplied by 60 multiplied by 50, and you get a very big number. And if you ever got a shock of the mains electricity, you notice it buzzes, whereas if you get a shock from a car battery, it burns you. And the power in direct current is actually more efficient, because there are no periods when there's no current flowing. Now, one of the things that's essential in order to get to grips with this is my videos. Now, I put up these videos in 2010. Now, there are ones where I talk on the board and show what's happening, and I've made those private for the minute because I don't want them to crowd out my new videos. But there are 3 videos there which are essential for anyone, and particularly students. And the reason why they're so reliable is that I actually use the equipment there and then. I actually use them. Val Martin Ireland, YouTube, Myth About Wind Energies. And the clips you're looking for is 1A, 1B, but particularly 1C. Just note that one. And that's well worth looking at, because I put a lot of effort into making that particular video. Without that, I'd have to repeat it all here, and if you won't look at it the first time, you're hardly going to look at it the second time. So, the 2 types of power in a battery, for example, in a battery, the type of electricity that's made is direct current. It's chemical, essentially. The chemicals absorb into 2 plates in the battery and produce positive and negative, and that's it. There's no alternation, no nothing. That will work a bulb or work any appliance, but it will not work a transformer. A transformer needs fluxed current. It needs to flux, and that's shown. I think it's clip 1B. That's shown. So there's a myth out there that you can transform battery power. You cannot. And as a result, you cannot bring battery power a way up or a way down in a transformer. Battery doesn't work in a transformer. So the next thing then you have to think about then is, when you generate electricity mechanically, you put a magnet going past a starter, a winding. And that is a transformer, except that the rotor inside can spin. There's no difference in a transformer and a motor, except the rotor can spin in the transformer. In the transformer, there's no rotor. So the core of the transformer is stationary. Now, so the current produced by an alternator is alternating current. And in the old dynamos in the cars, that's alternating current too, but it's transferred via brushes into direct current. Okay, there was the war of the currents that can be viewed online between Nikola Tesla and Thomas Edison. Now, one of the things is you cannot put alternating current and direct current together, because this is switching 50 times a second. You cannot put them together. You'll have a direct short. They cannot be connected indirectly. So if you want to mix the two, you have to you have to decide which one you want in the final outcome, and that's alternating current. Three-phase alternating current is what our grid runs on, all industrial motors runs on, and your household supply is a tap for two of those wires. There's three possible taps can be taken off it. You have one in an ordinary household supply. In a factory you have three. Okay, so when you have when you need an alternating current, and you then want to feed other current into it, you have to go through a certain process. Now, the problem with wind energy is that it's reliant on varying speeds depending on the turbine and the wind speeds. So you can't keep it at exactly 50 Hertz. Now, you can use electronics to keep it very close to that, but you can't have two different systems, and the wind is very dispersed all over the country, so it's not possible to pin it down. So you have to have a backbone, and that backbone is fossil fuel plant, either coal-fired, which takes 9 hours to start up, nuclear, which takes 24 hours to start up. It's all hot water that does the generating. Or you can have a combined cycle gas turbine where you have a turbojet engine like of an aircraft, more or less, and the flue gases run a boiler, and you have two generators. That's combined cycle gas turbine. And then you have open cycle gas turbine, which is just a jet engine, a jet plane engine essentially. You can have a diesel engine then, and you can have hydro. Now, all of these are strictly controllable. You can control the speed, and you can have gangs and gangs of generators running, and they all provide the frequency you need. Now, if you can imagine 8 horses pulling a stagecoach, and we'd say there's 10 for the sake of it because of the number of digits. So if they all pull together, they'll all even out the load. If this fella here wants to plough on harder, he'll have to pull the whole coaches, so he'll eventually discover he has to go back. On the other hand, if one lag's behind, the harness will be hitting him. So it's in all their interest to run at roughly the same speed. And it's the same with the gangs of AC generators, three-phase generators. There could be 40, 50 with rotors inside up to 16 to 30 tons, and they're flying round, and they eventually come into unison. When you want to bring in a new one, you run it a little faster. You run it a wee bit faster, and you slowly bring it in, and as it does, it pulls back with the load, brings it back and into line, and then you can apply the steam to it and bring it all up. So the duty controllers are constantly controlling the output of the fossil fuel or river hydro. It can be controlled as well, or pump storage if you have it. Whatever it is, they're constantly controlling that. But key to it is the big heavy rotors which maintain the inertia, and that's shown in the video, plus the rotors in industrial motors, big industrial motors, three-phase motors, they're running as well. And if you cut the power from the motor suddenly, it'll feed back. There's a current flowing back from the motor as well as flowing into it. And as you put on the load, that current flowing back reduces. It's called back EMF. So a motor and the generator are essentially the same. The only difference in a motor and a generator is the speed. So if you have a generator here driving a motor there, this motor will go around the same as the generator. If you speed this one up, it will speed this one up. So they're the same thing. So all that weight running into thousands of tons in the system, even in Ireland, keeps the inertia going. So that if there's a very sudden cut for some reason, they'll still keep going. You have a couple of seconds to play with before you have a crisis with the frequency. Now remember, the frequency is crucial. You have to keep it very, very close to 50 hertz, 50 frequency per second. And a 1% variation each side is 1/50th each side, and that's 2%. So 1% each side would be a 2% variation, and out of 50 that's 4%. So essentially on the Irish grid they keep it at 49.7 to 50.3. If you go onto the dashboard that they have to show it to you, I might have the thing here now. There's their EirGrid's dashboard. You can keep an eye on how all this is going. Now, when you have alternating current, and this is why I make the second video, it's like the timing belt of a car. There are cogs. If you look there on that, you'll see that there are cogs on that, and there's cogs on the wheel, and these fit exactly into each other. These fit, so there's no slippage. Okay. So if you have this pulley here driving another pulley over here, you'll have them running at exactly the same amount of cogs. They're in complete synchronization. So on a car, the crankshaft goes twice the speed of the camshaft, but there's not that big a pull on it. So a belt like this is adequate for a car diesel engine. Okay. Now if you want to increase the torque that these can pull, you just simply add more pulleys on the shaft and more of these, and you double each time, you double up the number of pulleys. Okay, so I've shown that here now on a diagram here on the wall. I don't know if you can see it. You see the pulley here driving this one, so that's synchronous. Now we have a different thing. Now we have a pulley, a belt like this, which is just an old fan belt. You see it there, and that runs on something like a wheel like this, around like that, and it can slip. So it's capable of slipping, right? Now that's similar to direct current, because if you have direct current and synchronous power, you can't connect them directly, but what you can do is you can aid this one. You can add to the load it'll carry, or the power transmitted, with a smooth pulley, but this must run slightly faster than this. So as the smooth one runs slightly faster, when you connect them, it slows down and slips a bit, bringing it into line. So the direct current can actually augment and add to the load that the system can carry. Now in reality, as I said, you cannot fit direct current and alternating current directly together. So what they do is they invert it. So a wind turbine or a wind farm produces AC current on the generator. It's conditioned then, and it's put into alternating three-phase current, and it's brought out to the substation, and it's connected there, right? So as long as the main backbone, fossil fuel power, is dominant, you can bring it up quite a lot. A system with 100% fossil fuel, synchronous power, would have way too much inertia. It would be more than enough to deal with it. So you can reduce the amount of fossil fuel and augment it with direct current, or with non-sequence power, as it's known as. It doesn't matter what it is, it's not in sequence with the whole grid. All the wind farms are given different frequencies. Now they are given a signal to make them run close to the grid frequency. Now, so the question is, how much wind can you let into the system? And 60% is what they're actually achieving sometimes at the minute, but at that stage you're walking on eggshells. I would have thought about 22 or 3% would be all you can bring in, and some people say 16%, but they can get 60%. But the problem with the 60% is that it's varying, and as it's varying, you're putting extreme pressure on the turbine of the fossil fuel plant, as it's inclined to ramp up and down, and it's like you operating the pedal of your car, revving it up and down, or revving a chainsaw with the trigger, or a lawnmower, or anything else. It runs better at a constant speed. So when you introduce wind, you have to ramp it up and down. Moreover, in some cases they get rid of the old heavy steam plant and replace it with jet engines, fast-acting jet engines and diesel engines, and these are less efficient, and the emissions go up. with the result that the wind has an adverse impact on the ordinary traditional generation. Okay, now it's difficult enough to explain this because the lay person will wonder how you can do all this, but you can bring in a frequency non-synchronous power, which is either direct current or alternating current, which is not in line with the main frequency. You can't bring it up exactly. The rotors in the system, in the motors that are running, and in the generators of fossil fuel plant are heavy enough to allow you to allow in a lot of wind. And so you can actually use the two. Now it's not that simple. It would be lovely if the non-synchronous power was smooth, conventional running continually. But if it were that, you wouldn't need non-synchronous. You could make synchronous power. So as you go rely on a whole lot of dispersed wind farms, the synchronization of the grid is lost. So you have this mix. You have the fossil fuel plant required there, and you cannot take it out. If you do, the trips will go and the whole lot will collapse. And that has been happening. That happened in London last week, and it happened in Ireland in February 2018, and it's very close. It's happening regular. So as you increase the amount of wind energy, or indeed solar energy, non-synchronous power, you begin to reach a point where you have to limit it. And the big indication here is, remember, you cannot run any grid system 100% on wind or solar. That is not possible. You can't do it because you can't get the exact frequency required that these heavy rotors require. Many people dispute that, but the blackouts have happened when it's tried to exceed it. You can do it, but you take a chance. And remember the definition of wind capacity credit, the usefulness of wind. The usefulness of wind is the amount of other generation that can be shut down and replaced by wind without endangering supply. And once you come close to endangering supply, you're at a problem where the grid operators have to restrict the amount of wind coming in. So that's that. I'll leave that for now, thank you, and we'll go on now to 17.2 and we'll develop on this a little bit more. Okay, thank you.